Welcome to PNU Talks, teaching and advocacy for lifetime knowledge and skills.
Good day everyone, I am Cristel Ann Idkilang Bantugan, taking up Bachelor in Science Education with specialization in Physics.
And I am your learning from home buddy for this episode. Today, we will be learning the law of universal gravitation and how it was formulated by Sir Isaac Newton.
Before we dive into our topic for this episode of PNU Talks, let me share to you some trivia about an apple.
According to Reader's Digest, there are a long list of benefits that we can get from eating apples. Here are some of those benefits. Number 1, eating apples help our teeth become whiter and healthier as apple stimulates the production of saliva in our mouth, reducing the tooth decay by lowering the levels of bacteria. Number 2, it avoids Alzheimer's. Study shows that drinking apple juice could keep Alzheimer's away and fight the effects of aging on the brain. Number 3, eating apples also help reduce cholesterol. The soluble fiber found in apples bind with fats in the intestine, which translates into lower cholesterol levels. Number 4, it detoxifies our liver. Our liver is responsible for clearing the toxins out of our body. Many doctors are not convinced of the fat detox diets, saying that instead of giving good benefits, these detox diets have greater potential of doing harm to our body. Good news is that we don't have to spend that much to have our livers detoxified because it was found out that eating fruits such as apples help detoxify our livers. Number 5, eating apples boosts our immune system. Red apples contain quercetin. This one is an antioxidant that can help boost and fortify our immune system, especially when we are stressed out.
We can get lots of benefits from eating apple, but it doesn't just end there. Did you know that an apple has an immense contribution in the field of physics? And it all started when Sir Isaac Newton sat under an apple tree.
Just like an apple, Newton's law of universal gravitation is of great significance, and in this video, we will find out why. But first, let us have a quick flashback before we talk about Newton's law of universal gravitation. During the prehistoric times, they still don't have a concept of gravity.
All they know is that Earth attracts objects near its surface, and that is the reason why when we try to drop or when we try to release an object near the surface of the Earth, it falls on the ground.
It was Sir Isaac Newton who introduced the concept of gravity. According to some legends, Newton was resting under an apple tree, then suddenly a fruit fell on his head. At that moment, he made realizations on his head and came up with the law of universal gravitation. While according to some sources, the more correct version of the story was that Newton was actually observing the apple from its tree.
And upon observation, Newton realized that the speed of the apple's motion is changing as it falls towards the ground. In physics, we call that one as change in velocity.
When we say velocity, we are referring to the speed of the motion and the direction to which an object is heading. And we can say that there is a change in velocity if there is a change in speed, or a change in direction, or a change in both speed and direction.
Since the apple's speed of motion and its direction is changing, its velocity is changing. And when the velocity of an object is changing, that object is accelerating.
Acceleration by definition is the rate of change of velocity of an object with respect to time. So just remember that when you hear the term acceleration, we are talking about how velocity is changing with respect to time.
When an object accelerates, there must be a force that causes the acceleration. We know that a falling object accelerates towards the Earth because of the gravitational force of attraction between Earth and the object.
Newton concluded that gravity is dependent upon distance. According to Newton, force of gravitation between Earth and other object is inversely proportional to the distance separating the center of the Earth and the center of the other object. Take note that we are not talking about this distance or this one. We are referring to the distance separating the centers of the two objects. In simpler terms, the lesser the distance, the greater the gravity. The greater the distance, the lesser the gravity.
Newton realized that yes, gravitational force is inversely proportional to distance, but distance is not the only variable affecting the magnitude of the gravitational force. So what is the other factor?
To answer this question, let us analyze Newton's observation with the apple. As the apple landed on Earth's surface, Earth and apple applied equal force, and that is based on our understanding on gravitational force. Now, which of the two has greater acceleration? Is it Earth or the apple? Based on Newton's second law of motion, net force is equal to mass times acceleration. Hence, acceleration is directly proportional to the net force and inversely proportional to the mass. Meaning to say, the lesser the mass of an object, the greater it accelerates. And the greater the mass of an object, the lesser it accelerates.
Since the mass of the Earth is much greater, it is the apple that accelerates more. So the apple accelerates towards the Earth.
Let us emphasize this statement which I mentioned earlier. The greater the mass of an object, the lesser it accelerates. And earlier, we had tackled that an object accelerates due to force. Hence, we can say that force must also depend upon the mass of an object. Isaac Newton figured out that mass is another factor which affects the magnitude of the gravitational force. Mass is the quantity of matter in an object. It is also the measure of inertia of a material object. So the greater the mass of an object, the greater is its inertia. But what do we mean by inertia? Inertia is the tendency of things to resist changes in motion. So the greater the mass of an object, the greater is its tendency to continue doing whatever it happens to be doing unless a force is exerted upon it. And that is based on Newton's first law of motion. And according to Newton, mass is directly proportional to force. So for Newton, the force of gravity acting between the Earth and any other object, which can be represented by F sub g, is directly proportional to the mass of the Earth. It is also directly proportional to the mass of the other object and is inversely proportional to the square of the distance separating the object centers.
While Newton was figuring out his law of universal gravitation, he could only calculate the relative gravitational force in comparison to another force. That is why he added a universal gravitational constant to his equation, which is represented by a big G or a capital G. He has no idea about the exact value of G, but he was sure that it is a tiny number.
It was Henry Cavendish who discovered the value of the gravitational constant. Henry figured out that the value of the big G in Newton's equation is 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. Newton's second law of motion tells us that the net force is equal to mass times acceleration. So we have net force is equal to m times a. While Newton's law of universal gravitation is trying to say that if the force is due to gravity, the acceleration that we are referring to is a gravitational acceleration. So we have gravitational force is equal to mass times gravitational acceleration. And our gravitational acceleration is equal to the universal gravitational constant multiplied by the mass of the bigger object divided by the square of the distance separating the centers of the two objects. So now we have here the formula for law of universal gravitation. We have net force due to gravity is equal to mass times the gravitational acceleration. So we have our F sub g, or the net force due to gravity, is equal to the mass of the smaller object multiplied by the gravitational acceleration, which is equal to gravitational constant multiplied by the mass of the bigger object divided by the square of the distance separating the centers of the two objects. So this formula could also be written this way. So we have F sub g, or the gravitational force, is equal to our gravitational constant multiplied by the mass of the two objects divided by the square of the distance separating the centers of the two objects. The value of our gravitational constant is 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared. Remember that the unit of force is Newton, which can be represented by a capital letter N. To check our understanding, let us try doing some problems related to our topic, which is the law of universal gravitation. You can pause this video if you want more time to solve these problems. So we have here problem number 1. Determine the force of gravitational attraction between the Earth having a mass of 5.98 times 10 to the power of 24 kilograms and a 70 kilogram physics student if the student is standing at sea level, a distance of 6.38 times 10 to the power of 6 meters from the Earth's center. All we have to do is to multiply the gravitational constant, which is 6.67 times 10 to the power of negative 11 Newton meter squared per kilogram squared, to the mass of the Earth, which is equal to 5.98 times 10 to the power of 24 kilograms, and the mass of the physics student, which is equal to 70 kilograms. The product will be divided by the square of the distance from Earth's center, which is equal to 6.38 times 10 to the power of 6 meters. So our final answer is 686 Newton, and that is the force of gravitational attraction between the Earth and the 70 kilogram physics student if the student is standing at sea level. Problem number 2. Determine the force of gravitational attraction between the Earth having a mass of 5.98 times 10 to the power of 24 kilograms and a 70 kilogram physics student if the student is in an airplane at 40,000 feet above the Earth's surface. This would place the student at a distance of 6.39 times 10 to the power of 6 meters from the Earth's center. Again, we just have to multiply the universal gravitational constant to the mass of the Earth, which is 5.98 times 10 to the power of 24 kilograms, and to the mass of the physics student, which is 70 kilograms. In this problem, the student is in an airplane, so the distance from the Earth's center is greater compared to the previous problem wherein the student is standing at sea level. So for problem number 2, the value of the distance is 6.39 times 10 to the power of 6. Our final answer is 684 Newton. This is the value of the force of gravitational attraction between Earth and the 70 kilogram physics student if the student is in an airplane at 40,000 feet above the surface of the Earth. We can observe that in these two problems, the force of gravity acting upon the 70 kilogram student or the student's weight is less on an airplane at 40,000 feet than at sea level. This illustrates the inverse relationship between separation distance and the force of gravity. Problem number 3. Suppose that two objects attract each other with a gravitational force of 16 Newton. If the distance between two objects is doubled, what is the new force of attraction between the two objects? So let us first analyze the problem. We know that the magnitude of the gravitational force varies inversely as the square of the distance between two objects. So since distance is doubled, therefore our d is equal to 2d. And we have to square 2d, so we have 4d squared. Therefore, if the distance between the two objects is doubled, then the gravitational force will be lesser, decreasing to 1/4 of the original value. In this problem, the original value of the gravitational force is 16 Newton. So since the original value will be quartered, so we have 4 Newton as our new force of attraction. In a nutshell, law of universal gravitation asserts that any particle of matter in the universe attracts any other with a force varying directly as the product of the masses and inversely as the square of the distance between them.
We can actually relate our topic today, which is the law of universal gravitation, to the current happenings in our lives.
Law of universal gravitation tells us that gravitational force is inversely proportional to the square of the distance that separates the center of the Earth and the other object. In other words, the greater the distance, the lesser the force.
We can actually relate this one to social distancing. The greater our distance from each other, the lesser would be the force of infection, meaning to say, the lesser would be the rate at which susceptible individuals acquire the coronavirus.
That is why we are told to practice social distancing, especially that the number of cases here in our country is increasing day by day. The best thing that we can do to help our frontliners is to follow the protocols in our respective localities.
From Newton's formula, gravitational constant is represented by a big G. And in our lives, we also have a big G who is constant.
He never left us but even promised us everlasting life. I know that you know who I am referring to. Of course, He is our Almighty God. Know that in everything that you are facing right now, He is in full control. All we have to do is to trust in Him.
Amazing how we were able to insert life lessons as we discuss this science-related topic, just like how amazing Newton was when he discovered the concept of gravity by observing the apple falling from its tree. I hope you have learned something from this episode. If you have questions, just comment it down below. I'll try my best to answer them. And that's it for this episode. God bless everyone.